On 4.3, listen, we have some points to make about acids and conjugate bases, the way Ka, Kb, and pKa and so forth work. So we have a list of Kas up here and the Kb of ammonia, but they want us to arrange these by pKas, but we have Kb. Well, if this was a base, it is a base. If it acted as a base, it would take another H on itself and it would turn into NH4 plus. So this is the conjugate acid. This is the thing that has a Ka. So don't say that you have a Ka of ammonia. You don't. The Ka of ammonia is so small it's not worth discussing, even by our standards. This, however, does have some ability to donate H plus to water. Its Ka is not large, as we see, but it is something that is worth discussing for the purposes of this class. So how do we find the Ka? We take Kw over the Kb value they gave us, and that gives us Ka. And what they don't mention in here, and so I went and typed it back in, but I wrote it here, is you get Ka by doing negative log of Ka. And I say a P number is always negative log of whatever you were talking about. So pKa is negative log of Ka. And so we take negative log of this, or sorry, this, and we get pKas. Now, the thing to notice about this is that because it's the negative of the log, it's like pH and that the order reverses. And in fact, the pKa of HCl is just, I mean, it's really, really small. Why is that? Because the Ka of HCl is darn near infinite. Why is that? Because the Ka of HCl is darn near infinite. I mean, how much of this is ever going to reattach? This is the reaction, right? Making H plus and Cl minus. How much is ever really going to come back? And the answer is just, even by our standards, just nothing. So you get a numerator that's exceedingly large in the Ka value and a denominator that's very, very, very small. And so it just approaches infinity. On B, what they don't say here, but they are doing, I figured out, is rating Kb. So we get that by dividing Kw by Ka, or in this case, they just furnished it. And because it's not a P number, and we didn't use negative log, a bigger value is a stronger chemical. So these are getting bigger, bigger. This is slightly bigger than that. And they're getting bigger because bigger is less negative. Look at the exponents. And so these are getting a bigger, and that's a better base. So the conjugate base of a strong acid is neutral. And, like we said before, we discussed this. If you get that, right, how likely is that to be a base? I mean, nothing, right? Just nothing. So that thing's not going to affect the pH of water. However, if you have a weak acid, it does have some ability. And of course, the stronger the acid is, the weaker its basic characteristic. The stronger acid it is, the worse base it is. If it wants to give the H plus away, then it doesn't want it back. And so as one goes up, the other characteristic must go down. On example 2, they want to revisit the idea of whether dissolving these salts in pure water, because that's what an aqueous solution means, will create an acidic, basic, or neutral situation. I keep having an argument with the writers of this workbook about whether calcium hydroxide is a strong base, and I've seen some notes on the internet that claim it is, but I looked up the Kb and I just can't believe it. So to avoid the argument, I am changing this to K and this to Na. So you dissolve this and you get 1 K and 2 Cl minuses in water. The K is unable to attract an OH minus to it because that would be forming a strong base in water, which can't happen. That's why it's a strong base, because it comes apart in water. And the Cl minus attracting H plus to itself would be forming a strong acid in water, which can't happen because that's what strong acid means. It comes apart in water. So this would have no effect. However, F minus does attract an H plus. Back here, the Ka is something small enough to matter. In other words, if it is not that great at giving away H plus, doesn't it also attract it somewhat? And the answer is it does. And if you're getting rid of H plus out of water, you're creating a basic solution. And they mean that it's basic because of the F minus. Here we have something that is definitely going to be acidic in water and something that cannot remove H plus cannot act as a base, so this will definitely create an acidic solution. And in this case, it's a contest because this one will be acidic and this one will be basic, reference the previous two. But the K value of NH4 is greater than the K value of F minus. So in the end, you get an acidic solution. On number three, it took me a moment to figure out what they're doing, so I've written this out to be a little bit more clear. This reaction can be separated into these two half reactions. However, what we know is Kas, and this is not acting as an acid, it's been flipped to be a base. So if we're going to use the base version of this, where it's taking an H on, we can't use the Ka, we have to use the inverse, where instead of this being in the numerator, it's in the denominator under 1. And then we can multiply the appropriate Kas. Remember, we're going to invert this, and we get the K for the overall reaction, which is greater than 1, which means this is product favored. When you run it this way, it is favored because K is greater than 1. On page 2, we talk about phosphoric acid, which is a triprotic acid. It has 3 acidic protons, 3 acidic H pluses, because it's that formula. Now, the key here is that the acidic protons, all 3 of them here, they could all come off, but they don't come off nearly as easy as each other. They are not equally acidic. Notice the Kas are very different. So the first one comes off pretty easily, the second one not so much, and the third one not much at all. Even by our standards, that's a low number. And they mean Ka here, not just K. Effectively, that's Ka, because what else is this going to do? It's going to act as an acid. So we can use all 3 Ks and find what the pH would be. Now we know the beginning molarity here, and we have none of this and none of that. So some of this gets destroyed, making one of these and one of those. One of these makes one of these and one of those. And so here's our equilibrium amounts. We can put them into our K expression. And the little wrinkle is here, this K is big enough that we cannot cross out minus X. And I did it, and when you do cross out minus X, you get 2.7, which is enough to complain about. And you end up with the quadratic formula. And I actually went and used the quadratic formula and I put it into a solver online, and you do get their answer, but you have to use the quadratic formula. And crossing X minus X out is a little bit too much cheating. However, this is X. So X is the H plus amount, right? Well, for the second proton coming off, now we have H2, PO4 minus 1. We have a starting amount of H plus because it was this amount. And one of these getting destroyed creates one of these and one of those. Here's our equilibrium amounts. However, Ka now is so small that we can cross out plus and minus X, and we get an X value. The X value is this amount, right? X is the value of this chemical, which carries on here. So this X value goes in here. We destroy one of these, creating one of these and one of those. Remember that when we said crossing out plus X won't matter, that means that adding in X won't matter. So this number is unchanged and carries on here for H plus. So subtracting X and adding X gives us these values, but the Ka is really small, even by our standards. So again, crossing out minus X and plus X won't matter. And we can solve for just this X and get that value, which again is so small that subtracting this from that, or adding it to this here and subtracting here, simply will not matter. So notice the interesting thing here is that the H plus didn't change for the ripping off the second and the third H. And so the H plus molarity depends only on the first association. And so effectively the pH didn't change after the first release of the first H plus. So the pH remains constant really here, and you don't really even need to run these numbers. They matter so little that you won't notice the difference. So there's no point. You just can't notice. So what's the point in doing all that work and worrying about it? So when the Kas get small like this, they won't matter. They're inconsequential compared to this. So why is K1 bigger than K2, which is bigger than K3? Because this gets more and more negative, and it holds on to the H pluses better and better. And so it's releasing it worse and worse, and the Ka goes down for each successive case.